Hey guys, a recap from where we ended off last time. So, four parameters are important for corrosion to take place. Number one, there has to be two different metals. Number two, these two metals have to be separated on a galvanic series. That means they have to have different potential. And between the two, the most anodic one will be the one that corrodes, the one with the highest negative charge. Number three, these two metals have to be in contact. And finally, there has to be an electrolyte, and an electrolyte is made up of a combination of moisture and salty ions. So, moving on, there are several ways corrosion can take place. So, this will be the different types of corrosion, if you like. The first form in which corrosion can occur would be a uniform attack. This one refers to a piece of metal corroding on the surface in a uniform manner. A stress corrosion, if you remember, I mentioned this to you guys before about if you bend a piece of metal at that place where the metal is bent, that place is regarded as high energy because it has a combination of tensile forces and compressive forces. So the high energy makes it susceptible to corrosion. That would be the typical stress corrosion form. Then the one we just saw now is called the galvanic corrosion, which involves two different metals being in contact. And notice that it is a type of corrosion out of many types, but we mentioned the four things that are key for corrosion to take place. That means, in addition to this being a type, this can happen in other forms as well. For instance, in selective leaching, those four parameters are still important or still apply in that it is one metal. If you take brass, for instance, brass is made up of copper and zinc, which are both metals, but brass is an alloy. So the two different metals parameter thing still applies here as well, because between the two metals, selective leaching is a type of corrosion where between those two, zinc in this case, more negative compared to copper, it will be the one that corrodes, but it's one piece of metal. So do not think of the two metals being involved being only physically two different metals, even if you don't see that, because metals generally are used as alloy, and alloy is made up of more than one element. If we're talking physically two pieces of metal, then it will be this type, galvanic type. Hopefully that makes sense. There is also intergranular or intercrystal. Again, this one, if you remember when we introduced the topic on metals, I spoke about how crystals form and come together in the crystal structure and form a grain next to a grain. Where the grains meet, that area again is regarded as a high energy. And similarly, because of the high energy that you saw with the bent part, it is a high energy area where corrosion is likely to take place. There is also pitting corrosion. This is the one that you would find in most cases on the coastal areas where there is a salty environment. So the way it happens is that there is salt ions in the atmosphere that attack pieces of metals in such a way that the metal will have pits and holes in them like that. So that is called a pitting corrosion. There is also crevice corrosion. This one refers to in cases where you have joints not flashing properly, not joined together such that there are crevices, or if you were welding two pieces of metal and then there are cracks in there that are left and not sealed properly, that is likely to lead to crevice corrosion. And then last but not least, there is erosion corrosion, which basically just means corrosion resulting to the flow of fluids, like an entire stretch layer of a metal gets corroded away such that it is weakened because of the reduction in thickness. You guys have to know these types or these forms of corrosion. It's very important, not only in a hypothetically a test, but for you guys as designers and thinking of making products out of metal, because you have to factor these things in. You should know what is likely to happen in these different ways. So why is corrosion so bad? It affects the mechanical and physical properties of products or of metals, which effectively means affecting your products. So corrosion is bad because it results in a loss of strength. Why? Because it leads into a weakening or reducing the thickness of metal, and then sometimes even complete structural failure occurs. It leads to the weakening of parts. As you can imagine, if products or structures fail, there is likelihood of injuries and fatalities to some extent. And generally, products do not function optimally because of corrosion. So corrosion is not only bad in terms of mechanical and physical properties of products and structures, but it is also just as bad for the environment. Why so? Because it leads to contamination, likely if the products or metals are coming into contact with the stuff that we eat. And again, harmful pollutants and toxins can be leached into the environment. And then again, as you can imagine, if these products and structures fail, it is not only costly, but it also calls for an ongoing use of scarce resources, which now we need to continue to use to make new products or to even maintain them. So then what do we do? There are several control and protective measures that can be done, and I've listed a few here, and we're going to go through each of this in detail. They include sacrificial protection using design features to control or to prevent corrosion, anodizing, and that one already you can tell from the introduction of this topic, where we said the anode is the one that will corrode if you have two metals. So if you're anodizing aluminium, you can already tell you are protecting aluminium with something that is going to corrode, which is anodizing instead of aluminium corroding. But we will look at this in detail. And there can be protective coating mechanisms, which is just painting or using plastic coating to your products. There are also self-protecting metals, and most of the time corrosion is associated with high temperature, so reducing temperature can be used as a control measure if you can. Sometimes people also use inhibitors. So let's look at the first one, which is the sacrificial protection, also known as cathodic protection. Remember, we said between the two metals involved, the anodic one, the anode will be the one that corrodes. So if this is a cathodic protection, what it means is you sacrifice a specific metal to protect the one that is important to you, which in this case will be a cathode. So this is done through a process called galvanization, which refers to the application of zinc coating onto steel, for instance. So if you want to use steel but you want to protect it, they do it through the cathodic protection by covering with a zinc coating. That helps in that if the environment is very corrosive, corrosion will take place onto the zinc coating instead of the steel. So that is cathodic protection or sacrificial protection, in that you're sacrificing zinc to protect steel. Another example of a cathodic protection will be in situations like where you have to join metal with a metal, such as using rivets to join sheets of metal. So cathodic or sacrificial protection, in that you know which one will corrode based on the galvanic series, its potential. So whichever one is more anodic that you know is going to corrode, that is the one that you will need to use as the actual joint, not as the product. In that, if your sheets of metal are more anodic compared to the rivet that you are joining with, that means the anodic product, the anodic sheets of metal that you're joining are going to corrode, because now it comes into contact with another metal with a different potential. So doing the reverse of that is a sacrificial protection, in that you will need to protect your product by joining them with a piece of metal, that in this case the rivets, that have to be anodic. In that way, if the environment is corrosive or corrosion has to take place, it will chew on the joint, which is maintainable, as opposed to chewing on the actual sheets of metal that you're joining. Again, hopefully that makes sense. Design features as the means of preventing or controlling corrosion. This again, you probably will be familiar to you guys, because you use design features to solve problems or different processing techniques, like in injection molding or casting. I mentioned the design features again that you need to look out for in casting. So the similar thing here, using design features. This means if you had to, say, join pieces of metal again, like with rivets, this kind of setup would be a poor setup that is likely to be attacked by corrosion. Why? Because there's likelihood of crevices forming in this type of joint. So you would rather join these two sheets of metal in a way that they flush properly, like that, or like this. So this is a design feature, designing things maybe to be joined in a different way compared to using rivets to prevent any formation of crevices, because that will lead into corrosion. And I put several examples here, and again you can tell why. For instance, if it's a product that has to contain fluids, this design is poor compared to that one, because the moisture can get trapped there instead of flowing through easily. And there are a lot more examples you guys can think of.